Okay, so where we left off, we spent a couple of different times we've looked at solving equations. You know, things like, come on, 3x minus 6 equals 24. And of course we solve that by doing what? Adding the 6 gives us 3x equals 30. Then what? We divide by 3. X equals 10. And we have looked at some applications using formulas and some story problems even where we had to create that equation and use it. You know, we've had story problems like the perimeter of a rectangle is 2 times the length plus 2 times the width. And problems like the perimeter of a rectangle is 86 feet. Find the length if the width is 19 feet. Where would I start there? Tell me what to do.
Multiply 19 times 2 and then subtract that answer from 86 and then divide by 2.
Okay, so you could just work through it knowing how the rectangle fits together. You just work through it without writing the formula, and that is fine. Especially when we're starting out with simple word problems, a lot of times you know how to solve it without the equation. So writing an equation can be almost more confusing because you have to do it. Let's use the formula for this one. P equals 2 times the length plus 2 times the width. Substituting in here, what would go in for P?
86.
86, good. 2 times L, or are we going to do anything there?
No.
No. So that's just going to stay 2L. 2W, are we going to do anything there?
Yeah, we're going to substitute the W with 19.
We got it. We're going to put the 19 in for W, so 2 times 19. Now before we start to solve this, what do we have to do? Combine the 2 times 19, which is 38. So 86 equals 2L plus 38. Come on now. What's next?
So we need to subtract 38 from either side?
Yes, now we can start to solve by subtracting the 38. So we get 48 equals 2L. That 38's gone. And then divide by 2. So that's gone. 24 equals L. So we got a length of 24. Should always make sure we go back and see if that's what we're asking. Yeah, find the length. So that is what we're looking for. The length is 24 feet. And technically we should rewrite it as length equals 24 feet. Or just 24 feet. Really should not leave it as just 24 equals L. I won't mark it wrong if that's what you do with it at this point, but you should get used to starting to label your answers. And we discussed that there are 3 types of problems out there. One type of problem is we have 2 amounts. I'm going to say amount A plus amount B equals a total. There are 2 things that add up to make a total. We have amount A minus amount B. We have 2 things that subtract to make a difference. And we can have two amounts that have to be equal to each other. Amount A equals amount B. Well, what we're going to look at today is we're going to look at how some of this applies to geometry. Well, we're not going to get into proofs or anything like that. We're just going to get into some of the very basics in this course. In fact, we touch on it, use it for algebra, then we circle back around to it later. And then in our last couple of weeks, we'll look at areas and volumes specifically in a geometric application. But for right now, I want to look at the geometric side. And I want to start out from the very basics. The most basic concept in geometry is this thing right there. It's just a point. And all it does is indicates a location. It has 0 dimensions. Well, since I told you it has 0 dimensions, I should probably talk about what a dimension is for just a second. A dimension is a measurable characteristic of the ran out of space there, and usually it corresponds with direction. So 0 dimensions, there's just literally 0 directions that you can measure this object in. If I take a point I'm going to call it point A here. And if I take that point and I drag it across the surface, now I'm going to call that point B. I'm ending at point B. What I have created there, a lot of people would call it a line, but technically it's a line segment, because a line should go on forever in both directions. Now, in practical application, a line isn't really practical because everything in practical applications kind of has a starting point, and a line does not. So when we use the phrase line, usually we are talking about what's technically called a line segment. Some quick things about our line segment. Number 1, notation. Just write the end points A and B with a little line segment over the top of them. That means line segment or segment AB. Now, we just created that segment by dragging point A. So for us, that line segment makes sense to be called AB because we started with A and we went to B. But if you see it on a piece of paper, usually you have no way of knowing which point came first and where it started. So calling it segment BA is perfectly acceptable. Because once it's created, that direction of movement is kind of gone. The length of that line segment is equal to the distance the point moved. And since now we do have a measurable length, this is 1 dimension. We can measure it in exactly 1 direction. Now, a little later on in the course, we're going to take that 1 dimension and move up into 2 dimensions. We're going to take a line segment like that. And we're going to drag it in a second direction. Now, a concept in math is the concept of perpendicular. Perpendicular just means at a right angle. It's a little bit more powerful than that because it means at a right angle in every measurable direction. But we'll talk about that more later. We could take that segment and move it in a second direction perpendicular to the first one, at a right angle to the first one. Oops. My mouse is jamming up today. Oh, let's do it this way. I move it at a right angle or perpendicular to the first one. Now, if you think of like dragging a stick across the sand, across the dirt sideways, it leaves its trail as you drag it across. That traces out a rectangle. And the size of that rectangle, of course, depends on the length of the original segment and that distance that we dragged to that segment. We will talk about area a little more later. But for right now, you need to know that this is 2 dimensions. It's measurable in 2 directions. Also, it was created to create this from a point. You have to drag that point in 2 different directions to create it. So that's why it's 2-dimensional. We could take that rectangle or that 2-dimensional object. So there's my rectangle. I'm just looking at it from kind of an angle, so it looks like it's squished a little bit. And if I take that rectangle now, and I drag it in a 3rd direction, perpendicular from both of the first 2, I now get 3 dimensions. It would be a volume, yes. This is 3 dimensions because I've now moved in 3 directions. And yes, I have created a volume. And of course, the size of that volume depends on what the area was of that rectangle we started with, and again, the distance that we moved it. We're going to come back and talk more about areas and volumes later. For now, I want to go back to that point again. We'll go back to point A. And once again, we are going to drag that point in a single direction. This time, however, I am not going to stop. I'm going to keep going on forever. This creates what we call a ray. And this ray might go through several other points. It might go through point C and D and whatever. So for notation, to name a ray. Now we said in the line segment it didn't matter which point we used. We had to use the end points, and we could use either end point first because we didn't know what direction it was dragged. There's nothing to indicate it. In a ray, do we know which direction it's been dragged?
Yeah.
Yeah, we know it started at A and went out. So that starting point always has to go first. Now it goes through several other points here, in this case 2 other points. We can name either one of those. So we can call this ray AC. So a little arrow above it is ray. We can call it ray AD. The first point must be that starting point A, and the second point can be any other point along that ray. A ray has a couple of different properties. First is the location of the starting point. Which for our purposes, the location, we're not into grids yet. So location at starting point, we're going to define it as to be the starting point of everything that we're going to do for now. The second is it has a direction. the way direction is defined is it actually goes back to navigation. Used to be pretty common that most people knew a little bit about navigation, but in the last 100 years or so, it's not much of a common piece of knowledge anymore. But it kind of goes off a grid. Yeah, this would be east, north, and so on. But east is defined to be 0 degrees. North was defined to be 90 degrees, and so on around the circle. Of course, 360 would be back at east or back at 0. So the direction was from this. So if I put AC on here, the direction of AC is just that angle right there. Now, we're not going to get into measuring angles in this class. So let me just tell you, I'm going to tell you that's 21 degrees or so. So the direction of ray AC is 21 degrees. It's going off in that direction. Okay. Now, if there's something called vectors as well that look very similar to rays. Vectors not only have a starting point and a direction, they also have a magnitude, which is their length. So it doesn't go on forever. It goes a certain distance. Even though there's an arrowhead on it, it doesn't go on forever. We're just talking about rays where it's just the direction is all that we have to worry about. Well, the reason I'm making such a big deal about the direction of a ray, excuse me, let's take a ray. We'll have ray AC again here. And let's say I go back to that original starting point, back to point A. And I'm going to drag it in a second direction. We call that ray AF, going through point F there. What I have created now, having two rays with the same starting point, that is called an angle. That common starting point, by the way, is now going to be called a vertex. Now, many of us have measured angles before. You know, the angle is your rotation between the two sides here. The technical definition of the size of an angle comes from this direction up here. So let's put angle AF on here, or ray AF on here, I should say. Let's say it goes like that. And let's say its direction, let's call that 68 degrees. The angle then between them, that's this angle right here, is the difference in direction. So this one's at 68 degrees, this one's at 21 degrees. The difference is 47 degrees. So that's a 47 degree angle. Now, as I said, in the last 100 years or so, navigation hasn't been a common tool. We have all sorts of other things that allow us to get from point A to point B. We don't need to understand, the navigational directions. You don't need to pull out a compass and know what it means to go head at 40 degrees north of west, things like that. You don't need to really know so much anymore. So we've kind of come up with an alternative definition for an angle. If I start out moving in a direction and I turn all the way around, how many degrees is that? 360 degrees. Perfect, exactly. One complete turn is 360 degrees. So if I start out going in a direction and I turn around, so I'm going exactly the opposite direction. How much is that? 180 degrees. How did you get that? 360 divided by 2, right? Just cut it in half. We're divided by 2. A portion of a full circle. If I'm going in a straight line and I turn to make a square corner or a right angle, that is 90 degrees. How'd you get 90 degrees? 360 degrees divided by 4 gave you 90. So what we have done basically, the same exactly what we've done here, is we've defined each angle as a fraction of a full turn. So since a square corner is 1/4 of a full turn, it's 1/4 of 360 degrees, or 90 degrees. So we have some possible relationships between angles. The first one I'm going to talk about involves a common starting point. But instead of having 2 rays, I'm going to have 3 rays coming off of this. So here we have 2 angles that share 2 things. One, they share a vertex. The vertex of both angles is angle A. And they also share a side. What's that?
Would that be C then?
Well, I haven't defined what the angles are, have I? These are what we call adjacent angles. Now, someone here had asked me, is angle AC the side that's shared? Well, it depends on what 2 angles we're looking at. Or side AC, is that the side that's shared? Well, it depends on what angles we're looking at. If I were looking at this angle here, first of all, how would I specify that I'm looking at that angle? Well, that would be angle. We name one of the sides, or a point on one of the sides. Then we name the vertex, which is A. Then we name a point on the other side. So I could call that angle BAC or angle CAB, either one. Doesn't matter which side I name first, but the vertex has to be in the middle. If there's more than one point on each side, it doesn't matter. I can pick any of those points on the sides to name it. If my second point or angle is this one, can somebody name that angle for me? CAD or DAC. Perfect. If those are the 2 angles, then a side AC is the shared side. But it wouldn't have to be, because there's actually another angle formed here. That one could be referred to as angle BAD or DAB, either one. And I could say that the 2 adjacent angles are really those 2. BAC and BAD. Now the shared side would be, that's the side they share. It'd be, yep. Adjacent angles have some interesting properties. The biggest thing is that they are additive. Now remember, addition and subtraction work together. They're the same operation. So when I say additive, it implies they're subtractive too. Just subtractive isn't really a term. It's just additive. Additive implies both. Subtractive. Yeah, that one's hard. Say that one 4 times fast. So anyway, if I tell you that angle BAC is 38 degrees. Now, technically, rather than giving an angle BAC, we might put a little M in front of it. That M in front of it means the measurement of angle BAC is 38 degrees. Means the same thing either way. And if I tell you that the measurement of angle CAD is 33 degrees, that means the measurement of angle BAD must be what? Well, this is 38 degrees and this is 33 degrees. I add them together. So I'd add that up to you what? 71. 71 degrees. They are additive. And like I said, they could be subtracted as well. If I tell you that the measurement of angle OMD is 111 degrees, and the measurement of angle OMP is 86 degrees. So what does that mean? That means this here is 111, and this here is 86. Perfect. Measurement of angle PMD. This is going to be the 111 minus the 86, which is 25 degrees. We can come up with situations with these adjacent angles that are kind of special. We could have two adjacent angles that add up to make a straight line. Now I know some math teachers that if you say straight line, it's like fingers on the chalkboard because it's redundant. A line has to be straight, right?
It's not straight, it's curved.
Yeah, exactly. If it's not straight, it isn't a line. Let's say this angle over here is 62 degrees. What's this angle over here have to be?
62 from 90.
Careful. 180 minus 62. There we go. Has to be 118 degrees. How did we know they added up to 180? Because they formed a straight line. Two angles that add to 180 degrees or form a straight line are called supplementary. They do not have to be adjacent angles. If they are adjacent, it forms something a little more powerful called a linear pair. But if they're adjacent and they form a straight line, we know that they have to be supplementary. Now, along with that, if I make an angle and put that little box, that's actually a square that's being put in the corner there, indicating that is a square corner or a square angle or a right angle. And if I have two angles that add up to a right angle, if I know that this angle here is 68 degrees, what's this one here have to be? 90 minus 68, or 22 degrees. How did I know that it had to be 90 degrees? Because it's a right angle. Very good. Two angles that add to 90 degrees or make a right angle are called complementary. Now, if you're anything like I used to be, I could remember the words supplementary and complementary, but it can be kind of tricky to remember which one's which. The way I remember it is you get complements when you are right.
Right angle.
Yeah, so it's a right angle. Another relationship between angles that we have arises actually from the supplementary angles. If I have two lines that intersect like this, if I tell you that this angle here is 32 degrees, can I find that angle? What is it?
Yeah, because you've got
32 from 180.
Perfect. 180 minus 32 gives us 148 degrees. Because this is a line here, those two angles add up to a straight line. They're going to be supplementary. So that angle has to be 48 degrees. Now I want to look at this angle over here. How do I find that one?
Minus 148.
Perfect. 180 minus 148 is 32 degrees. That angle is 32 degrees because that's a straight line. Those two are supplementary as well. They have to add up to 180. Well, notice these two angles are equal. Those two are what we refer to as vertical angles. Vertical angles are formed by intersecting lines, and they must be equal. When two lines intersect, there's actually always two pairs of vertical angles formed. We have the 32 and the 32, but there's also going to be another 148 down here. Very good. So those two are vertical angles as well. There's two ways of looking at vertical angles. One is if you think of, the line starting out as a single line and picking a point and rotating around that point to create this angle here. Well, the amount of rotation here has to be the same as the amount of rotation over there. The second way of thinking about it is both this angle and this angle here have to be supplementary to that angle, the 148. So two angles that are supplementary to the same angle have to be the same, have to have the same measurement. Okay. How are we going to use these relationships? Well, we might have a situation like this. I might ask you to find each angle. I know this angle is 9x and this angle is 3x. What is the relationship between those two angles?
They both relate off that one line.
Should equal 180.
There we go. They are supplements. They form a straight line. So those two angles have to add up to 180 degrees. Remember we said there's three possibilities. They add up to a total, they subtract to make a difference, or they're equal to each other. Once we have it in this form, what can we do with it?
Add the 9 and the 3.
Yep, 9x and 3x make 12x. Then what? Divide by 12.
180 by 12.
There we go. 180 divided by 12 is 15.
15.
Perfect. All done, right? Let's move on to the next one. No, what do we have to do?
12.
We have to answer the question, was find each angle. We know x is 15, but that's not the angle. This angle is 9x. That's going to be 9 times 15, otherwise known as 135 degrees. This one's going to be 3 times 15, or 45 degrees. Now we're done. We have both angles. If I give you a situation like this where we have a right angle, we have a smaller angle in here, and I have angle x there. But I'm not going to ask you to find x. I'm just going to ask you to write an equation for x, or to find x. What's the relationship here?
X equals 180 minus 29.
Not 180.
Oh, 90.
90.
You could do x equals 90 minus 29. That works. These two angles are complementary, and technically the relationship is x plus 29 equals 90, right? The two angles add up to 90. So either one of these is okay. This one you've actually taken one step towards solving it already. You've done the minus 29. So this is what I was saying before. Sometimes you look at these and you know what to do to find it. So stepping back and writing an equation can be difficult because you already know the answer. So be patient with yourself on those. So what's the relationship here?
Equal 180.
They add up to 180. Very good. So 2x plus 11 plus 5x plus 19 adds up to 180 degrees. What do we do with this one before we can start to solve? Combine the 2x with 5x gives us 7x. Very good. We're adding them, right? Then we got the 11 and the 19 makes 30. Very good. Then what do we do? Subtract 30. So 7x equals 150, and I can see I screwed this one up a little bit, but that's okay. We'll make do. What do we do next? Divide by 7. If you punch that in your calculator, 150 divided by 7, it's going to tell you that that is something like 21.428571429, something like that. So we're not going to plug it back in to find the angles because I screwed up. It happens. So let's take a look at this one. This one here is going to be 2x minus 7. And this angle over here is going to be 3x plus 37. And this is a right angle, even though I didn't get it drawn real square. Our relationship here
Should equal 90.
should equal 90. 3x plus 37 plus 2x minus 7 equals 90. Where do we go from there?
5x times or plus 30.
So 3x and 2x make 5x. Good. We combine the 37 and the negative 7 to be a positive 30. Then what?
30 from either side, so 5x equals 60.
Perfect. We subtract 30 from each side, gives us 5x equals 60. And then divide by 5. So x equals 12. Now I will go back and find the angles here. I didn't necessarily say what I was looking for here, but let's find the angles. So 3x plus 37 is 3 times 12 plus 37. And now it's order of operations. 3 times 12 is 36 plus 37. That's 73 degrees. Over here, 2x minus 7. Well, 2 times x is 2 times 12. Minus 7. 2 times 12 is 24. Minus 7, that's 17 degrees. And now I can double check. Do those two add up to 90?
Nope.
Yes, they do. What's my relationship here? Do they add up to something?
Should add up to 180.
Well, yeah, be careful. These two are vertical angles. And what do we know about that relationship? They're going to be equal.
Oh,
So our 3x plus 11 has to equal our 4x minus 2. So now to solve here, what do? I have to get rid of one of the x's, right? They're on opposite sides, so I can't just combine them. So I subtract the 3x, yep. So I get 11 equals, what's 4x minus 3x? 1x, or I can just put an x, right? And I have the minus 2. So then what? Add 2. So 13 equals x. All done? Nope, we got to come back up here, put 13 in for x, and find what each of those angles is. So 3 times x is 3 times 13 plus 11. 3 times 13 is 39 plus 11. That's 50 degrees. Let's double check to make sure we get the same thing over here. 4 times x will be 4 times 13 minus 2. Well, 4 times 13 is 52. Minus 2 is 50. So we do get the same thing on either side. So that's really the tough part of these, is recognize what is the relationship and then just putting them in the equation. We had briefly mentioned the area of a rectangle. And we said the area of the rectangle depends on the length of that original segment. We define that to be the length of the rectangle. And the distance that that segment was moved. Well, that distance is equivalent to the width of the rectangle. So the area of a rectangle is equal to the length times the width. So if I tell you that a rectangle with a length of 18 inches has an area of 90 square inches, find the width. Well, we know our formula. Area equals length times width. Right? Do we know any of those numbers, any of those values?
Yeah, the area is 90,
The area is 90.
and the length is 18.
The length is 18, so L is 18. So instead of A equals L times W, it's 90 equals 18 times W. What do we do from there? We divide by 18. Very good. You get that 5 equals W, or W equals 5. So the width is 5. What unit goes on there? Inches. And technically, this division here, the 90 divided by 18, technically what that was 90 square inches divided by 18 inches. So we divide the counts. Oops, I don't know where the 91 came from. 90 divided by 18. 90 divided by 18 is 5, but then we also divide the names. Square inches divided by inches is just inches. We also have volume. Volume was taking that rectangle, that area, and moving it through space. So it is the area of the original rectangle times the distance moved. So yes, volume is length times width times height. By the way, if you're struggling to draw out a cube like that or a box like that, the easiest way to do it is just draw a rectangle, then draw another rectangle slightly offset like this. Okay, connect the corners. I didn't do a very good job there, but there's a reason I'm a math teacher, not an art teacher. Put it that way. An alternative definition, by the way, is that the volume is equal to the area of the base. That's the area of the rectangle times the height. Length times width is the area of a rectangle. All you're doing is just combining them first. This formula gets used in geometry more because you can find the area of stuff that isn't a box. It can be a cylinder, it can be an odd shaped base, or whatever. Find the required height of a box with length of 12 inches and width of 8 inches if the desired volume is 480 cubic inches. So in our formula here, V equals L times W times H. What do we know? Do we know V?
Yes.
Yeah,
480.
480 cubic inches. So I'm just going to put in 480 for now. Do we know L?
Yes.
12 inches. Very good. Do we know W?
Yes. 8 inches.
8 inches. Do we know H?
No.
We better not, or there's nothing left to look for, right? So, do we have to do anything before we go on with this?
Multiply the 12 and 8.
Perfect. We do have to combine the 12 times 8, which is 96. Good. So that's 96H. 480 equals 96H. Then what?
Divide.
Divide by 96. You got it. 5 equals H. So the height is 5 inches. What do you think? I think you guys have had enough for the day with the test already. There is no quiz today, but there is a homework.
When does it due?
That homework is due, it should be due on Thursday.
Thursday noon.
Yes. I was just double checking, making sure I didn't change anything. But yes, it is due Thursday at noon. Tests I should have graded. It all depends on when I receive. I've received New Richmond's. I haven't checked email here in the last half hour to see if I've received Ashland's yet. But I should receive them by noon today, and I'll get them graded. The grade will appear on Blackboard as soon as I have them graded. For those of you here in Rice Lake, I will give them back to you on Thursday. For those of you at Ashland or New Richmond, I will email them directly to your WITC email. So you will have it in your email before, sometime between now and class on Thursday. Now, with that said, when your tests are graded, you're not necessarily done with them yet. Once I have graded your tests and passed them back to you, I do offer you the chance to correct the problems you got wrong. So if you would like to redo the problems you got wrong, when you do redo them, when you do corrections on them, I do require that you show your work there. I don't require you to show your work on the regular test, but I do require that you show your work for the corrections. And if you do those and turn them in, if you get them right, I will give you back up to half your points. Now, I say if you get them right, I don't want you to turn them in unless you're sure they're right. So, I mean, for the corrections, I don't care if you work with a friend, if you work with another teacher, or if you come to me. If you cannot figure out how to do it, I would be happy to sit down next to you and walk you through it step by step. So, I mean, one of the purposes of that is I want to make sure that you've at least seen how to do the problem correctly before you're done, and so that you have it down. So make sure you have them all correct before you turn them back in for corrections. So we will talk about that more on Thursday once everybody has their tests back. You guys have a good day, and we will see you on Thursday.
Are you going to be around for a little